So, welcome to our next controls workshop on full state feedback. So, kind of before we get into any of that, we're going to talk a little bit about stability analysis, which I'm sure you remember doing just stability, right?
What does that mean?
So, if it helps, I will go back and bring up the stability and control. The
Yes.
what we're talking about with stability back here.
Yes.
Neat. So, one thing that is useful is that when we have a linear dynamical system, we can actually tell mathematically whether or not it is stable. And specifically, the way this is done is if you look at the A matrix, if and only if all the eigenvalues of the A matrix have negative real parts, then you can guarantee that your system is stable. And this also extends to nonlinear systems that are linearized about a point. In any case, in a more general sense, just on the complex plane as a whole, depending on where the eigenvalues of A lie in the complex plane, that changes how the system dynamics behave. There's a derivation for this, but I'm not going to cover it. And also the eigenvalues are often referred to as the poles of the system. But in this diagram here, this is the complex plane. You remember doing imaginary numbers, right? In math?
Yep.
Yeah, so essentially each is kind of showing if where the poles are at and what that means for the system. So you can see on the right hand of the system, you have things like that, the purple dot, where if your poles land right there, you can see the system kind of goes away from your point. It's unstable. Whereas on the left, you have everything kind of converging to zero, and that's stability. And you can kind of see there's different types, different kind of like modes of stability where we have both the underdamped and overdamped flavors. And you can see it depends on whether or not you're on that axis or not. So I just wanted to give you kind of a good reference for what that means. This will come in handy later on. So now, a brief, this is kind of a side note, but there's another part of the linear dynamical system that we haven't covered yet, which is the output represented by Y. That's effectively your end output, basically. And this is because, we don't always care about every state, and sometimes we need to modify it to get the value we care about. And you can see here, this is the full linear dynamical model where you have x dot equals ax plus bu and y equals cx plus du. C is the output matrix, and that determines how x is transferred. So oftentimes you might usually it just ends up being in the most regular sense, you just have an identity matrix, which would essentially just mean that y directly corresponds to x. Sometimes you might have an identity matrix, but some things are zero, which is essentially just saying y is mostly x, but with some variables omitted, perhaps because they can't be measured or you don't care about them, whatever. That's usually what you'll see. D is the feed forward matrix. For the most part, that's zero. You don't really need to know what that is for now. Just so I'm just including here so you have an idea, so when you see it later, you're not confused. Now we can go on to the fun stuff for today. So full state feedback. So full state feedback control is a common method for controlling MIMO systems. And on the right, you can see we have our nice diagram, which I'm sure you kind of remember the PID diagram. This is kind of a similar way to that, in that we have, our whole system represented as a, whatchamacallit? I guess, well, one thing I realized, this says plant on it. Plant is oftentimes just that's a common term for talking about your system that you're controlling. And I think that comes more from like industrial type processes where, you're controlling a plant to like have a certain temperature or something for chemicals or whatever. That's kind of where it comes from. In any case, it's called full state feedback because you're feeding back the entire state vector to the control, rather than PID where you can only feed back. PID, you're only sending back one number, and that's kind of what's controlling it. Full state feedback is the whole thing. Sometimes we read it as FSF. So to kind of get more specific, our FSF controller equation is U of t equals R of t KR minus KX of t. K is what is known as the gain matrix, and that is a constant. And the dimensions of a K are such that it ensures that when you multiply K by X, you get the proper dimensions of the control input. And later on, when we get to tuning FSF, that's basically kind of like the PID constants. That's the thing that we get to decide. Also, we have R of t, which is the reference signal, and that's essentially what allows us to define a set point. And that's scaled by a constant matrix K of R, similar to K, just so that you have it in the same, dimensions so that you can do that subtraction. Actually, before I move on, do you have any questions about just the FSF equation?
So you're explaining it how like PID returns like one variable?
Yeah, so typically, yes?
Well, this returns, it looks like it returns a matrix.
Yes, so basically PID, you have, so this is actually one thing that whys can be used for, is if you have, say, a system that has more than two dimensions, you might have something, you might have the output equation such that the output is a scalar, and then that scalar is what's fed to PID, and that's what decides your control input. Whereas this, it's always your entire state. It's kind of circumventing the output, basically.
Okay.
I guess I probably could use with the example picture with PID and the output equation, but I could look that up later. But yeah, continuing on. So what we could do with this is, because we know from, if you remember from earlier in the slides, we know that the stability of the system is determined by the A matrix. So we can actually look at how FSF affects that. And so here we could just see a quick derivation where we have our system dynamics, and then we substitute in the FSF control equation that U equals RKR minus KX. And after doing a little bit of rearranging, we get X dot equals, in parentheses, A minus BK times X plus BRKR. And effectively now, that A minus BK is our effective closed loop A matrix. It's essentially the A matrix of our controlled system. If you were to imagine as if the system just naturally behaved in that way. So does that kind of make sense how we're getting this effective A matrix and what it means?
Yeah, I think so.
Rad. So what we can now do is we can get to the tuning of this, because with our system dynamics being controlled by that, we can then determine the stability of that controlled system by finding our effective A matrix. And because we can select K ourselves, we could select any element in K. We can, by extension, decide where all the poles are in our A matrix, where all the eigenvalues are, pretty much. And this is why FSF is also known as the pole placement method. And so, essentially, the goal is to choose a K matrix such that you move all the poles from where they naturally are over to over to the left onto the stable side of the complex plane, the negative side, that is. So yeah, that's kind of the gist of it. Does that kind of make sense? That went a lot faster than I was expecting, to be honest.
I think it makes sense.
All right. Now I'm going to do a nice abstract example. I have a nice system right here, which this is a linear system. The first thing I'm going to have you do is determine whether or not the system is stable, and then design a full feedback controller to make sure that it's both stable and overdamped. Oh, that's a typo. Basically make it overdamped about the origin. This in black. Okay. And you can actually do this analytically, although I won't make you hand calculate eigenvalues if you don't want to. Do you have a preference for how to do it?
I have totally forgotten how to solve eigenvalues.
Yeah, so you can, if you, one thing you could do is you can just analytically, using I think it's called the characteristic equation, analytically solve for values of K to place the eigenvalues in specific locations. For right now, though, I'm not going to make you review eigenvalues. You're welcome to just do it in MATLAB and use a bit of trial and error to try and put K, or try and get it stable and whatnot.
So I would can you go back a couple slides?
To where?
It was in the beginning where like it reviews like what is considered a stable state.
Oh yeah. Basically, so essentially anytime you take the eigenvalues of something, oftentimes you'll end up with a complex number. And the important part is that the real part, i.e. the part of your complex number that's not being multiplied by I, is negative.
Okay. The eigenvalues of x dot?
The eigenvalues of the A matrix, specifically.
Okay.
And remember, because the A matrix is a constant, there's a numerical, or there's an analytical solution to get an exact number for our eigenvalues.
Well, don't we just want a negative real number or does, right?
Yes.
Negative real number.
Yeah, so that's the thing though, is because, you know, do you remember generally what eigenvalues mean significantly?
No.
All right, I can. It's been so long since I've taken linear algebra.
Hold on. I should have my notebook for it. Oh, never mind. It's somewhere in a box.
Everything's in a box. Yeah.
I
So
remember like using like setting up the diagonal as like lambda minus number or something.
have you ever found the eigenvalues in MATLAB? It's very easy.
I have not.
There's in MATLAB, there's literally a command just called eig, and it does it for you, and it's great.
Okay, so I just need to put in the vector. I mean, yeah, the matrix. Let's see.
Oh yeah, eigenvalues are. That's how you. Uh, Eigenvalues are the values in the matrix such that you get it to scale constantly. I think I'm saying that wrong, but if you want to review eigenvalues later, I recommend watching the 3 blue 1 brown video about them because that's honestly the only reason I know what an eigenvalue is.
These videos are great. Okay, let
They're
me.
so good.
I will share my screen. Okay. Ike. Like that.
Yep. So now if we let's just real quick just run that.
Okay.
We get that. And each element is there is one of the eigenvalues of the system. So before we get into doing the control, what I'd like for you to do is just first set up a thing to simulate this system over like 10 seconds or something.
Wait a second. Are these two separate real eigenvalues, or is this a combination of a real and imaginary?
Those are two. MATLAB will display it as an imaginary value if it is.
Okay.
Those are both real eigenvalues.
Okay.
One is negative, one is positive.
Yes.
Because that positive one exists there, it is then not stable. There's a
Mhm.
part of the system that will blow up and take it away from that point of equilibrium.
Okay. Okay. So, what did you mean by designing this system? I know.
Well, so first, let's just go ahead and make a thing to simulate that linear system over 10 seconds or something, just with like OD45.
Okay. 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 Um. Hmm. Let's do some copy pasty.
Yeah, OD45 it's always set up in a pretty similar way. So
Okay. X, T, and X. Okay, that's fine. This do I need? Uh,
I don't know. I guess you could just pick like maybe like 2 is your X naught.
2, 2. How do you know that that will be the dimensions of the initial value?
So the reason I know that that's the dimension of the initial value um, is specifically a too long vector. If you look at the A matrix, it's 2 by 2. Because you have to multiply A by X, they have to share the same dimensions. And just A is defined as being the length of X, a square matrix that has the same like width as X, basically.
Wait, so X is also a matrix.
X is a vector. Well, I guess a vector is technically a matrix, but
It's a 2x1,
yes.
and it becomes a. What does it become? Rows. It becomes a 2x1 afterwards. Oh, and then U is. What are the dimensions of U?
In this case, oh, wait, let me look at the example I had. So in this case, U is what is U?
It has to have one column. Wait, A. No. What am I saying? It has to have one row. It's a 1x2?
Yeah. So
Yeah, it's 1x2.
let's start off by just not including U. That's
Okay.
first. I want to just simulate just the system dynamics.
Okay.
Yeah, it's pretty simple at this point.
It's a 2x1, so.
So recall, you're not supposed to put the initial conditions within your function there.
Right. Okay.
Yeah.
And then we will bring this thing. Uh-oh. P. Wait a second.
So let's start off by just going like 1 to 10, just so it's a little smaller. So you can see it's very unstable. It quickly like explodes out to like 4.5 times 10 to the fourth.
Yeah.
So now we can go about adding our control.
U. Is that second thing? The second constant? Is that called B?
Yeah, B is also a constant. Do you remember what this significance of B is basically? It's
Well,
basically determining how the control is,
how strong it is.
what
Or
effect
how
it
it
has
acts.
on each of the parts of the system.
Okay.
Basically, what this B is saying is, U controls X1 but doesn't affect X2.
Yes. Okay. And then you had this equation for U somewhere.
Yeah, so I'll copy paste that for you.
Thanks.
So in this case, because we just want to go to the origin, our reference signal is just 0.
Our reference signal K?
So that R of t, that's just 0. Because
So-
we want it to go to the origin.
Can you explain why?
So the reference signal is pretty much just the set point. I suppose I probably should have mentioned that that's more or less a synonym. Reference signal is more referring to like a function that describes the set point over time, basically. So in some applications, you might want your set point to change, but in this case, we want it to stay the same. And because we want it to go to the coordinates 0, 0, the origin, what we're just going to do is just say, what should we call it? We just want it to be 0, because then x will be tending to go to 0.
I don't really understand, but I'll take your word for it. So,
I guess just to kind of try and explain it a little better, if you wanted it to go to the point 1, 1, that's your reference signal. It's now R of t equals 1, 1, basically. And you might have, if you want it to change over time, you might do R equals 1, 1 times t, and now it's your set point is following that line, basically.
what do you mean by set point?
So set point, this was I guess it's a vocab word from one of the previous things. Set point is basically the desired state of our system. Okay. So that's what we're controlling the system to do, basically. In this case, our set point is 0, 0, which means we want our system to move to 0, 0. That's the goal. Right now, uncontrolled, it won't. It won't ever go to 0, 0. Your set point could be a set velocity or a specific position and velocity. It could be whatever you want your state to look like.
Okay. I see. Okay. So x of t is already a matrix. And then k is...
One thing real quick, we should plot both x1 and x2, because right now you're just plotting x, which I guess is plotting x1. I'm not really sure.
Oh.
Do you want to just add
like this?
Yeah, and then you could add another plot for x2.
Oh no, I'm gonna let's have another graph. Ooh.
U. Oh, because you put in U, but you haven't defined it yet. Do you want to just, in your control, do you want to just remove that real quick and then... That looks a little weird. Oh, because you're doing... It's got to be colon comma 1, because MATLAB.
Oh, because this means the first row?
That's a... Yeah, because it's a 2D matrix, so you have to give both coordinates.
Got it.
There we go.
Yeah. They move in very similar ways. They move in identical ways.
What's that last thing? Oh. Never mind.
Wait. Hold
realize
up.
you put them on the same plot.
They're identical. Why does that make sense? Does that make sense?
It might just be how the system moves. That's what it seems like.
Let me change this number like real quick. Okay. It just happens to work that way.
It just yeah.
Okay.
All right. It's gonna U.
And then K is some matrix that we gotta assign, right?
Yeah. So K. This is something we're gonna have to do as a separate step. Basically, is picking values of K and finding the what that makes the effective eigenvalues of the matrix.
Oh, and that was another slide that you had, right?
Yeah.
Can you show that slide as well?
Yeah, I can throw that in. I'll throw in the nice derivation just so you have an idea.
Okay.
So the important equation on that slide is the one on the bottom.
Yes. So I see what you're doing. I don't see how this becomes the effective eigenvalue. Because that's just now I would say like the effective A matrix.
Yeah, so you get the effective A matrix, and then you can find the eigenvalues of that effective matrix. And that's basically, think about it this way. If you have your system that you're controlling, if you were to have, if the control was just built into the system somehow, you basically end up with your system would have that effective A matrix, basically.
Okay, so but we would have to find the eigenvalues of the A minus BK matrix.
What was that?
Since we have the effective A matrix, we have to find the effective eigenvalues.
Yes. And so if the eigenvalues of that effective matrix are both have negative real parts, or I should say all of them are negative real parts, that means that it will then have whatchamacallit, that means that your controlled system will be stable. And so one thing real quick, this is something that this is kind of a step you do like separately beforehand. So it's
So we're
not
just
part of
testing
the loop
values
here.
of K until we find something that we like?
Yeah, so the correct way to do this would be to use the characteristic equation to mathematically determine the values of K to get the poles that you want. But if we want to be lazy, we could just use, in a script, just do trial and error to get it right.
Okay. And then well, if A is a 2 by 2, B times K has to be a 2 by 2. So C has to have 2 columns. K has to be a 1 by 2. Right?
What was that?
K has to be a 1 by 2?
Yep,
Okay.
I think so.
Wait. What? Mm. Okay. Is it okay to have imaginary numbers?
Yeah, so let me throw something. Do you mind if I take over screen sharing for a moment real quick?
Yeah, go ahead. I have
All
to.
right. So basically what that means is because you have imaginary numbers, that basically puts you in this area of the complex plane, where both your real parts are negative, right?
Mm-hmm.
That means that your system will kind of follow this sort of path, where it's underdamped and it'll oscillate until it settles down.
For both positive and negative imaginary numbers?
So whenever you have the actual, like, whether or not the imaginary part is positive or not, that doesn't matter. All that matters is that the real part is negative.
Okay.
Um, the kind of end goal of the problem, let me check. The end goal of the problem is to have it be overdamped, so basically on the line. But we could do that step next.
So that would mean that you wouldn't need, you would have to get rid of the imaginary number to get an
Yeah,
overdeck
that would
system.
mean you want a pure real number.
I mean,
So we'll do
I
that next.
don't think guessing that's gonna take forever. I think.
Yeah, that's probably a bad idea. Okay, let's go back to. So you have your k values.
Okay. Let me share.
I think also after this, it is a good idea to just try seeing what different k values do to the response.
Okay. So this will work. And then U is equal to K times B times K. Wait. No.
It's
Wait.
equal to minus kx.
Oh, wait. Yes, you're right. Minus K times. And K is a function of A and B. Okay.
Yeah. So you do have to define k inside of that loop.
Yes.
So yeah. So
Oh.
ta-da! So you can see is what kind of what we expected. Oh, do you want to go throw a semicolon on the u?
Oh,
So that
is that why it printed it out? I was like, why are there so many U's? Okay.
the,
Ooh, that's cool.
all right. So you can see it behaves as we expected because we could tell that the eigenvalues were negative beforehand. We could guarantee that it will converge.
Yeah. Okay.
Do you want to see how changing k affects it?
Sure. Let's test something else. 5 and 5. Oh wait, no. I need to open this. Okay, we can try 5 and 5. Oh. Oh, so this component is overdamped. Maybe.
Do you want to put a y line in there?
Yes.
Do it on the top so it's on the bottom.
Do it on the top. Okay.
Sorry, that sounded weird. Do it before the other thing so it shows up underneath the other
I
lines.
0. Ooh.
I think it
It
looks
went
like it
under.
might be overshooting a tiny bit.
It does. Yeah, so it's not underdamped. No, it's not overdamped. It's definitely underdamped. Or
It's very slightly underdamped.
yeah. Okay, let's try something more drastic. Oh, okay, never mind.
Hey, so both real numbers, but unstable.
Yes. I'd like to see two negative numbers. That's not working. Oh, that keeps going up. Oh,
Hey,
okay. We can try that. 20 and -2. Ah,
would you look at that?
very cool.
So yeah. So, yeah. I think in general, out of the like basic control methods, I quite like full state feedback. I personally think it's nicer than PID, but PIDs you can't get simple than PID. It depends on what application you're doing.
Mm.
Generally, if you're doing a problem where you have a good number of variables and whatnot, and oftentimes you might have more than one control input, full state feedback's a good option. I know we used it it was my aircraft dynamics course. We used it for doing basically a autopilot for maintaining cruise pretty much.
Mm-hmm.
But yeah. So with that, do you have any questions about any of the stuff we covered today?
No, I think it makes sense.
Rad. Okay. With that, I'm going to stop recording. And